In electronics, the Darlington transistor is a compound structure consisting of two bipolar transistors connected in such a way that the current amplified by the first transistor is amplified further by the second one. This configuration gives a much higher current gain than each transistor taken separately and, in the case of integrated devices, can take less space than two individual transistors because they can use a shared collector. Integrated Darlington pairs come packaged singly in transistor-like packages or as an array of devices in an integrated circuit. The Darlington configuration was invented by Bell Laboratories engineer Sidney Darlington in 1953. He patented the idea of having two or three transistors on a single chip sharing a collector. A similar configuration but with transistors of opposite type is the Saclay pair, sometimes called the complementary Darlington behavior. A Darlington pair behaves like a single transistor with a high current gain. In fact, integrated devices have three leads, broadly equivalent to those of a standard transistor. A general relation between the compound current gain and the individual gains is given by, if beta 1 and beta 2 are high enough, this relation can be approximated with. Darlington pairs are available as integrated packages or can be made from two discrete transistors. Q1 can be a low-power type, but normally Q2 will need to be high power. The maximum collector current IC of the pair is that of Q2. A typical integrated power device is the 2N6282, which includes a switch-off resistor and has a current gain of 2400 at IC equals 10A. A Darlington pair can be sensitive enough to respond to the current passed by skin contact even at safe voltages. Thus it can form the input stage of a touch-sensitive switch. A typical modern device has a current gain of 1000 or more, so that only a small base current is needed to make the pair switch on. However, this high current gain comes with several drawbacks. Disadvantages. One drawback is an approximate doubling of the base emitter voltage. Since there are two junctions between the base and emitter of the Darlington transistor, the equivalent base emitter voltage is the sum of both base emitter voltages. For silicon-based technology, where each VBEI is about 0.65 V when the device is operating in the active or saturated region, the necessary base emitter voltage of the pair is 1.3 V. Another drawback of the Darlington pair is its increased saturation voltage. The output transistor is not allowed to saturate because the first transistor, when saturated, establishes full parallel negative feedback between the collector and the base of the second transistor. Since collector emitter voltage is equal to the sum of its own base emitter voltage and the collector emitter voltage of the first transistor, both positive quantities in normal operation, it always exceeds the base emitter voltage. Thus, the saturation voltage of a Darlington transistor is 1 VBE higher than a single transistor saturation voltage, which is typically 0.1–0.2 V in silicon. The increased low output level can cause troubles when TTL logic circuits are driven. Another problem is a reduction in switching speed or response, because the first transistor cannot actively inhibit the base current of the second one, making the device slow to switch off. To alleviate this, the second transistor often has a resistor of a few hundred ohms connected between its base and emitter terminals. The Darlington pair has more phase shift at high frequencies than a single transistor and hence can more easily become unstable with negative feedback.